On October 6, 1995, two astronomers, Michel Mayor and Didier Queloz, announced something that seemed impossible. They had been watching a star named 51 Pegasi. It was a sun-like star about 50 light years away from us. For years, scientists thought that planetary systems would look like our own. Small, rocky planets close to the star. Giant gas planets far out. That was the model. That was the rule. Mayer and Queloz found something that broke the rule. They detected a planet, but it was all wrong. It was a giant about half the mass of Jupiter, and it was orbiting its star in just 4 days. 4 days, our own Jupiter takes 12 years. This new planet, 51 Pegasi b, was closer to its star than Mercury is to our sun. It was a hot Jupiter. According to the models of how planets form, this could not happen. A gas giant could not form that close to a star. There wasn't enough material, and the heat and solar wind would blow the gas away. The discovery was met with skepticism. Some thought it was a mistake. Maybe the star was pulsating. Maybe it was a binary star system they were misinterpreting, but the data was solid. The planet was real. It was there. The discovery of 51 Pegasi b did not just add a new planet to our list. It forced an entire field of science to throw out its old books and start over. It meant that planets could migrate. They could form far out in a solar system and then spiral inwards over millions of years. You know, this idea had been around, but it was a fringe theory. Now, it was the only explanation. The universe was more strange and more violent than we had thought. Solar systems were not calm, predictable places. They were places of chaotic movement, of planets being thrown around like billiard balls. This one discovery opened the floodgates. Soon, astronomers were finding hot Jupiters everywhere. They were finding planets in egg-shaped orbits, planets orbiting two stars, planets that were nothing like what we have in our own solar system. The universe was not built in our image. Our quiet little solar system was the exception, not the rule. This is a story about a similar kind of discovery. It is about a time when astronomers pointed their telescopes at what looked like a simple, faint star. But when they looked closer, they found something that was not a star at all. They found something that should not exist. An object the size of a solar system that was shining with the light of a trillion suns. An object that was outshining its entire home galaxy. It was another impossible thing. And just like 51 Pegasi b, it completely changed our understanding of the universe. Number 16, they look like stars, but they aren't. The object known as 3C273 has a brightness that varies by about 30% over a period of a few months. When it was first cataloged in the late 1950s, it was the 273rd entry in the Third Cambridge Catalogue of Radio Sources. Its optical counterpart, seen with regular telescopes, looked like a faint, insignificant blue star, magnitude 13. A Dutch-American astronomer named Martin Schmidt was given the task of figuring it out in 1963. He was using the giant 200-inch Hale telescope at Palomar Observatory in California. He was frustrated. The object was a powerful radio source. That was strange for a star. Most stars are quiet in the radio spectrum, but the bigger problem was its light. When he took a spectrum of the object, a process that splits the light into its constituent colors like a rainbow, he saw a series of bright emission lines. These lines are like fingerprints. They tell you what chemical elements are present, but the lines from 3C273 did not match any known element. They were a complete mystery. For months, astronomers were stumped. They called these objects quasi-stellar radio sources, or quasars for short. They were star-like, but they were something else entirely. The breakthrough came when Schmidt had a sudden realization. He looked at the pattern of the lines, he ignored where they were on the spectrum, and just looked at their spacing. The pattern was familiar. It was the pattern of hydrogen, the most common element in the universe. But the lines were all shifted. They were moved far towards the red end of the spectrum. This phenomenon is called redshift. It is caused by the Doppler effect, the same thing that makes a siren change pitch as it passes you. In astronomy, a redshift means an object is moving away from us, and the bigger the redshift, the faster it is moving. The redshift for 3C 273 was enormous. It was 0.158. This meant it was moving away from us at about 16% of the speed of light, or around 47,000 kilometers per second. This was a shocking speed, but the implication was even more shocking. According to Hubble's law, an object's recession speed is proportional to its distance from us. A redshift this large meant that 3C 273 was not a star in our galaxy at all. It was billions of light years away. It was one of the most distant objects ever observed at the time. This created an immediate and profound problem. If it was that far away, then to appear as a 13th magnitude object in our sky, it had to be unbelievably luminous. It was not just bright, it was shining with the light of 2 trillion suns. It was about 100 times brighter than the entire Milky Way galaxy, which contains hundreds of billions of stars. Yet, it looked like a single point of light. A single star. This was the birth of the quasar puzzle. How could so much energy be generated in a volume of space that looked no bigger than a star? It defied the known laws of physics. Nuclear fusion, the process that powers stars, could not do it. There was no known mechanism that could explain this level of energy output from such a compact source. The discovery of 3C 273's true nature was a turning point in astronomy. It opened a new window into the extreme universe. It was the first piece of evidence for processes far more violent and energetic than anything humanity had ever conceived. And it all started with a faint blue dot that had a spectrum that made no sense, until one astronomer realized he was not looking at something strange, but at something familiar in a very, very strange place. Number 15. The light is an illusion of size. A quasar named PKS 1302-102, located about 3.5 billion light-years away, shows a predictable, repeating cycle of brightening and dimming every 5 years. The light from some quasars can double in brightness in a matter of hours. The fastest variations ever detected in a quasar suggest the light-emitting region can be no larger than the orbit of Jupiter. This fact alone was one of the biggest stumbling blocks in understanding these objects. After Martin Schmidt figured out the immense distance and luminosity of 3C 273, the puzzle deepened. The problem was variability. Astronomers continued to watch quasars and they noticed something odd. Their brightness was not constant. It changed, sometimes over a period of months, sometimes weeks, and in some extreme cases it could change significantly in just a day. This seems like a small detail, but it has profound physical implications. It is a fundamental clue to the size of the object emitting the light. Think of it this way. If you have a light source that is 1 light year across, and it suddenly flashes, you would not see the entire object light up at once. You would first see the light from the part closest to you, then, over the course of a full year, you would see the light from the more distant parts of the object finally arrive. The flash would appear to be smeared out over a year. The object could not appear to get uniformly brighter faster than the time it takes light to cross it. This is a hard limit set by the speed of light, the universe's ultimate speed limit. So, if a quasar's brightness can change significantly in, say, 1 week, it means the region producing that light cannot be larger than 1 light week across. 1 light week is a huge distance by human standards, about 180 billion kilometers, but in cosmic terms it is tiny. It is roughly the size of our solar system out to the Kuiper belt. This was the central paradox of quasars. The energy output was that of 100 galaxies. This suggested a massive object, something light years across. But the rapid variability proved that the engine producing this energy was confined to a region no bigger than our own solar system. How could you pack the power of 1 trillion stars into a volume of space so small? It was a contradiction that baffled scientists for years. It ruled out many early theories. Some suggested quasars were clusters of millions of supernovae going off at once. But a cluster like that would be huge, many light years across. It could not vary in brightness over a matter of weeks. The entire cluster could not coordinate its explosions to flash in unison. The light travel time argument was ironclad. It proved that whatever a quasar was, it was a single, coherent object, and it was incomprehensibly powerful and compact. This was the piece of evidence that pushed physicists toward more exotic explanations. They needed a mechanism that was far more efficient at converting mass into energy than anything seen before. They needed something that could operate within a tiny volume but release galactic-scale power. The variability was not just a curiosity, it was a clue that pointed directly toward the most extreme objects in the universe, the only things that could fit these contradictory requirements. It pointed toward gravity, not the gentle gravity of a star or a planet, but the crushed, warped, all-consuming gravity of a black hole. Number 14, the answer was the most extreme object known. The theoretical concept of an object so massive that light could not escape was first proposed by John Mickle in 1783. The term black hole was coined by physicist John Archibald Wheeler in 1967. The supermassive black hole at the center of the galaxy M87, the first to be directly imaged, has a mass of 6.5 billion times that of our sun. Its event horizon is larger than our entire solar system. The puzzle of quasars, with their galactic-level power coming from a solar system-sized region, demanded a radical solution. By the mid-1960s, a consensus began to form around an idea that was, at the time, still largely theoretical. The idea was a supermassive black hole. The concept of black holes comes from Einstein's theory of general relativity. The theory predicts that if you squeeze enough mass into a small enough volume, gravity will become so strong that nothing, not even light, can escape. The boundary of this region of no return is called the event horizon. For a long time, black holes were just a mathematical curiosity. But quasars gave them a reason to exist in the real universe. In 1964, physicists Edwin Salpeter and Yakov Zeldovich independently proposed that a supermassive black hole, one with the mass of millions or even billions of suns, could be the engine powering quasars. It was the only known object that was both compact enough and massive enough to do the job. A supermassive black hole solves the size problem immediately. A black hole with 1 billion solar masses would have an event horizon only about the size of our solar system. This fits perfectly with the light variability data that showed quasars must be small. But how does a black hole, an object famous for trapping light, become the brightest thing in the universe? The black hole itself does not shine. The light comes from the material that is falling into it. Imagine a giant cosmic drain. As gas, dust, and even entire stars get drawn in by the black hole's immense gravity, they do not fall straight in. They spiral inwards like water going down a drain. This spiraling material forms a vast, flat, rotating structure called an accretion disk. The energy does not come from the black hole. It comes from gravity itself. As material in the accretion disk gets closer to the black hole, it speeds up, moving at near the speed of light. The different layers of gas in the disk rub against each other at incredible speeds. This creates an enormous amount of friction, and this friction generates heat, unimaginable amounts of heat. The accretion disk becomes so hot, reaching temperatures of millions of degrees, that it glows with ferocious intensity across the entire electromagnetic spectrum, from X-rays to radio waves. It is this white, hot disk of infalling matter, not the black hole, that we see as a quasar. This process of converting gravitational potential energy into light is extraordinarily efficient. Nuclear fusion, the process that powers the sun, converts about 0.7% of a material's mass into energy. The accretion process around a black hole can convert 10%, 20%, or even up to 40% of a material's mass into energy. It is the most efficient energy generation mechanism known in the universe. It is the only process capable of producing the kind of power observed from quasars. The theory was elegant. It solved both the energy problem and the size problem in one go. The supermassive black hole provided the compact, powerful gravitational engine. The accretion disk provided the light. This model, proposed more than 50 years ago, remains the cornerstone of our understanding of quasars today. Number 13, it is not the black hole that shines. The innermost stable circular orbit, the closest a piece of matter can orbit a black hole without falling straight in, is 3 times the Schwarzschild radius for a non-rotating black hole. Matter in an accretion disk can orbit the central black hole at more than half the speed of light. To power a bright quasar, the central supermassive black hole must consume matter at a rate of about 1 to 10 solar masses per year. It is a common misconception that the black hole itself is the source of a quasar's light. The reality is far more dynamic. The light is a byproduct of a cosmic traffic jam on a scale that is hard to comprehend. The supermassive black hole is the gravitational anchor, the central engine, but the fuel and the furnace are in the accretion disk that surrounds it. This disk is not a simple, calm ring of matter like the rings of Saturn. It is a violent, chaotic whirlpool of plasma. It is formed from interstellar gas and dust that wanders too close to the black hole. Sometimes, an entire star can be torn apart by the black hole's tidal forces in what is known as a tidal disruption event, its stellar material shredded into a stream of gas that then feeds the disk. As this material is pulled from the outer edges of the galaxy towards the center, it conserves its angular momentum, causing it to flatten out and spin, forming the disk. The physics of the accretion disk is what makes a quasar shine. The material in the disk does not move at a uniform speed. And gas in the outer parts of the disk moves relatively slowly. Gas in the inner parts, closer to the event horizon, whips around at relativistic speeds, approaching the speed of light. This difference in speed between adjacent rings of gas creates immense shear and friction. This friction is the key. It converts the kinetic energy of the orbiting gas into thermal energy, or heat. The disk heats up, but not uniformly. The outer parts might be a few thousand degrees, similar to the surface of a cool star. But as you move inwards, the temperature skyrockets. The inner regions of the accretion disk can reach temperatures of hundreds of thousands or even millions of degrees. At these temperatures, the matter is a plasma, a soup of atomic nuclei and free electrons. It glows not just in visible light, but intensely in ultraviolet and X-rays. This is the source of the quasar's incredible luminosity. It is essentially the heat from friction magnified to an astronomical scale. The sheer amount of energy released is staggering. For a quasar to shine as brightly as it does, its central black hole needs to be fed a steady diet of material. A typical bright quasar consumes matter at a rate of a few suns worth of mass every single year. This infalling matter provides the raw material to be converted into energy in the accretion disk. The disk acts as a cosmic power converter, transforming the potential energy of gravity into the radiant energy of light with unparalleled efficiency. So, when we look at a quasar, we are not seeing the black hole, we are seeing the death scream of matter as it takes its final plunge. We are seeing a cosmic furnace, powered by friction and gravity, burning with the light of 1 trillion suns before its fuel disappears forever beyond the event horizon. Number 12, the jets move at almost the speed of light. The jet from the quasar 3C 273 is over 200,000 light-years long, significantly larger than the entire Milky Way galaxy is wide. The Galaxy M87 has a jet that appears to show blobs of material moving at 6 times the speed of light, an optical illusion known as superluminal motion. The total power carried by some quasar jets is thought to be comparable to the entire light output of the accretion disk itself. Not all of the matter spiraling towards a supermassive black hole makes it past the event horizon. A significant fraction, in about 10% of quasars, gets funneled away and shot out into space in two colossal, narrow beams called relativistic jets. These jets are one of the most spectacular and powerful phenomena in the universe. They are streams of plasma, mainly electrons and protons, that are accelerated to incredible speeds, often exceeding 99.9% of the speed of light. They emerge from the poles of the accretion disk, perpendicular to its flat plane. They travel in a nearly straight line for immense distances, sometimes hundreds of thousands or even millions of light years, far beyond the boundaries of their host galaxy. The exact mechanism that launches and collimates these jets is still an active area of research, but it is believed to be connected to the intense magnetic fields in the inner region of the accretion disk. As the disk spins, it twists the magnetic field lines into a tight, coiled structure like a wound-up rubber band. This twisted magnetic field acts like a cosmic particle accelerator. It grabs charged particles from the disk and flings them outwards along the black hole's axis of rotation at near light speeds. This is known as the Blandford-Znajek process. The jet is not just a gentle stream. It is a highly energetic, focused beam of matter and energy. When the material in the jet eventually collides with the sparse gas in intergalactic space, it creates enormous shock waves. These shocks heat the gas and cause it to glow brightly in radio wavelengths. This creates vast structures known as radio lobes, which can be seen by radio telescopes. These lobes can be many times larger than the host galaxy itself and are often the most prominent feature of a radio-loud quasar. The appearance of a jet can be deceptive. Due to the effects of special relativity, if a jet is pointed close to our line of sight, the blobs of plasma within it can appear to be moving faster than the speed of light. This is an optical illusion called superluminal motion. It happens because the blob is moving towards us at almost the speed of light, and so it is chasing the light it emits. Each subsequent flash of light it emits has a much shorter distance to travel to reach us, creating the illusion of faster-than-light travel. The existence of these jets adds another layer of complexity and power to the quasar phenomenon. They show that supermassive black holes do not just consume matter, they can also be cosmic engines that eject matter and energy back into the universe on a grand scale. These jets can have a profound impact on their host galaxy, blowing gas out of the galactic disk and potentially shutting down star formation. They are a visible manifestation of the extreme physics at play in the heart of a galaxy, a testament to the power of gravity and magnetism working together. Number 11. Some are loud and some are quiet. Only about 10% of all known quasars are considered radio loud, meaning they have powerful relativistic jets that produce strong radio emissions. The remaining 90% are radio quiet. A type of object called a blazar is a quasar where one of the relativistic jets is pointed almost directly at Earth. The first quasar discovered, 3C 273, is a radio loud quasar. Quasars are not all the same. While they all share the same basic engine of supermassive black hole accreting matter, they exhibit a range of different properties. One of the most fundamental ways astronomers classify them is based on their radio emissions. This leads to a simple but profound division: radio loud and radio quiet quasars. Radio loud quasars are the ones with the spectacular, powerful relativistic jets. And these jets, as they travel through space and interact with the intergalactic medium, generate intense synchrotron radiation, which is very bright at radio frequencies. These are the objects that were first detected by radio astronomers in the 1950s and led to the initial discovery of the quasar phenomenon. They account for only about 10% of the total quasar population. The other 90% are radio quiet. This does not mean they are completely silent in the radio spectrum. It just means their radio emissions are thousands of times weaker than those of their radio loud cousins. They still have the incredibly bright accretion disk shining in optical ultraviolet and X-ray light, but they lack the massive galaxy-spanning jets. The reason for this dichotomy is one of the biggest unsolved mysteries in quasar research. Why do some supermassive black holes launch powerful jets while most do not? One leading theory suggests it might be related to the spin of the black hole. A rapidly spinning black hole might be better at twisting the magnetic fields needed to launch a jet. Another idea is that it depends on the properties of the accretion disk or the amount of magnetic flux brought in with the accreting gas. It could also be an evolutionary effect where quasars go through both radio loud and radio quiet phases. Within the radio loud category, there is a special subclass of objects called blazars. A blazar is not fundamentally different from other radio loud quasars. The difference is simply our viewing angle. In a blazar, one of the relativistic jets happens to be pointed almost directly towards the Earth. This orientation has a dramatic effect on what we observe. Due to an effect called relativistic beaming, the light from the jet is incredibly brightened and focused in the forward direction. From our perspective, the jet completely outshines the accretion disk and the host galaxy. Blazars are among the most energetic phenomena in the universe. Their brightness can vary wildly on very short timescales, sometimes in just a few hours, because we are looking straight down the barrel of the jet and seeing the turbulence and shocks within it directly. The classification of quasars helps astronomers break down the problem and study the underlying physics. By comparing the properties of radio loud and radio quiet objects, they hope to understand the key ingredients needed to launch a jet. And by studying blazars, they get a unique and extreme view of the processes happening inside these cosmic particle accelerators. Number 10, they are beacons in the cosmic darkness. The light from the most distant known quasar, JO313-1806, took approximately 13.03 billion years to reach Earth. We see it as it was when the universe was only 670 million years old, just 5% of its current age. Quasars are so bright they can be seen with moderate-sized telescopes, even when they are billions of light years away. If the quasar 3C273 were located at the distance of Polaris about 430 light-years, it would shine as brightly in our sky as the sun. The immense luminosity of quasars makes them incredibly useful tools for cosmology. They are, in effect, the lighthouses of the distant universe. Because they are so extraordinarily bright, they can be seen from much farther away than almost any other type of object. Even the brightest galaxies, which are collections of hundreds of billions of stars, become too faint to see at the vast distances where quasars still shine brightly. This allows astronomers to probe the universe at very early times. When we look at a distant quasar, we are looking back in time. The light from a quasar that is 10 billion light years away has been traveling for 10 billion years to reach us. We are seeing that quasar not as it is today, but as it was 10 billion years ago when the universe was much younger. The most distant quasars are our only direct view into the cosmic dawn, the era when the first galaxies and stars were forming. These quasars act as cosmic probes. The light they emit travels across billions of light years of space before it reaches our telescopes. On this long journey, the light passes through whatever lies between the quasar and us. It passes through vast invisible clouds of hydrogen gas that fill the voids between galaxies. It passes through the halos of distant unseen galaxies. Each of these intervening structures leaves a subtle imprint on the quasar's light, absorbing specific wavelengths. By analyzing the spectrum of a distant quasar, astronomers can study the properties of the stuff that its light passed through. This technique turns every quasar into a background lamp that illuminates the otherwise invisible structure of the universe. It allows us to map the distribution of matter over cosmic history and study how that structure has evolved over billions of years. Quasars also provide a crucial reference frame for the universe. Because they are so distant, they are essentially fixed points in the sky. Their positions do not change perceptibly over human timescales, This makes them perfect for defining a celestial coordinate system. The International Celestial Reference Frame, the standard grid used by astronomers to map the positions of all objects in the sky, is based on the precise positions of hundreds of quasars measured with radio telescopes. In this way, these distant, violent objects provide the stable, unchanging background against which the motions of everything closer to us, from satellites to stars, can be measured. They are both the most dynamic and the most stable objects in our sky. Number 9. They let us read the universe's history book. The Lyman alpha transition of hydrogen corresponds to an electron falling from the second energy level to the first, emitting a photon with a wavelength of 121.6 nanometers. This wavelength is in the far ultraviolet. Due to the expansion of the universe, this line is redshifted into the visible part of the spectrum for distant quasars. The collection of absorption lines in a quasar spectrum is so dense it is called the Lyman alpha forest. One of the most powerful ways quasars serve as cosmological tools is by illuminating the Lyman alpha forest. This is not a real forest, but a pattern of features in the spectrum of light from a distant quasar. It is one of the richest sources of information we have about the large-scale structure of the universe. Here is how it works. The space between galaxies is not completely empty. It is filled with a tenuous, diffuse web of hydrogen gas, a remnant of the Big Bang. This is called the intergalactic medium. Now, imagine the light from a very distant quasar traveling towards us. On its billion-year journey, this light beam acts like a skewer, passing through hundreds of these intergalactic hydrogen clouds. Neutral hydrogen atoms are very good at absorbing light at a specific wavelength, 121.6 nanometers, a spectral line known as Lyman alpha. When the quasar's light passes through one of these clouds, the hydrogen atoms in that cloud absorb the light at the Lyman alpha wavelength. This creates a dark, narrow gap, an absorption line in the quasar spectrum, but here is the crucial part. The universe is expanding. A cloud that is farther away from us is receding from us faster than a cloud that is closer. Due to the Doppler effect, the Lyman alpha absorption wavelength for a distant cloud will be redshifted more than for a nearby cloud. So when we look at the final spectrum of the quasar, we do not just see one single absorption line. We see a whole forest of them. Each individual line in the forest corresponds to a different hydrogen cloud that the light passed through. The position of each line tells us the redshift of that cloud, and therefore its distance from us. The depth of the line tells us the density of the gas in that cloud. By studying the pattern of the Lyman alpha forest, astronomers can reconstruct a one-dimensional map of the distribution of matter along the line of sight to the quasar. It is like drilling a core sample through the cosmic web. By doing this for thousands of quasars in different directions, we can build up a three-dimensional map of the cosmic web and see how galaxies and gas are clustered. This technique has been used to measure the temperature of the intergalactic medium, to study the process of reionization when the first stars and quasars heated up the universe, and even to constrain the properties of dark matter and dark energy. The Lyman alpha forest is a remarkable record of cosmic history, and it is a record we can only read because of the bright, distant light of quasars shining through it. Number 8. Galaxies are sculpted by their central monsters. The outflow of gas from some quasars can carry away more than 1,000 solar masses of material every year. This is far greater than the rate at which the black hole is consuming matter. These galactic winds can reach speeds of up to 10,000 kilometers per second. It is now believed that the mass of a galaxy's central supermassive black hole is tightly correlated with the mass of the galaxy's central bulge of stars. For a long time, supermassive black holes and their host galaxies were thought to be separate entities. The black hole was a tiny object at the center, and the galaxy was the vast collection of stars orbiting it. The black hole was thought to be too small to have any significant influence on the galaxy as a whole. But we now know this is wrong. The quasar phase of a black hole's life is so energetic that it can have a profound galaxy-shaping impact. This process is called feedback. There are two main ways a quasar can affect its host galaxy. The first is through radiation. The accretion disk of a quasar is so intensely bright that the pressure of the light itself can be a powerful force. This radiation pressure can push on the gas and dust in the galaxy, heating it up and driving it outwards. The second, and often more powerful, mechanism is through the jets and winds launched by the quasar. The relativistic jets can punch clear through the galactic disk, but there are also wider, less focused winds of hot gas that are blown off the accretion disk. These winds can slam into the galaxy's interstellar medium, the raw material for forming new stars. This interaction creates a massive shock wave that can sweep through the galaxy like a cosmic tsunami. This process of feedback can have a dramatic effect on star formation. In a young galaxy, gas cools and collapses to form new stars. But if the central black hole becomes a quasar, the intense energy it pumps out can heat the gas throughout the galaxy. Hot gas cannot easily collapse to form stars. In the most extreme cases, the quasar-driven winds can be so powerful that they blow the majority of the galaxy's gas supply right out into intergalactic space. This effectively starves the galaxy of its fuel, shutting down star formation for good. This process is thought to be the reason why the most massive galaxies in the universe today are filled with old red stars and are no longer forming new ones. Their central quasars, active billions of years ago, blew out all the gas. This feedback mechanism also explains a mysterious observation, the tight correlation between the mass of a supermassive black hole and the mass of its host galaxy's bulge. It seems that the black hole and the galaxy grow together. The feedback process acts as a self-regulation mechanism. As the galaxy pulls in more gas, it feeds the black hole, which grows and becomes a quasar. The quasar then turns on and pushes the gas away, stopping both its own growth and the growth of the galaxy. This cycle ensures that the black hole never gets too big for its galaxy, and the galaxy never gets too big for its black hole. And quasars are not just passive residents of galaxies, they are active agents that, sculpt and regulate the evolution of their cosmic homes. Number 7, finding them requires sifting through billions of stars. The Sloan Digital Sky Survey STS, which began in 2000, has discovered and measured the spectra for more than 500,000 quasars. The upcoming Vera C. Rubin Observatory is expected to find more than 20 million quasars over its 10-year survey. Quasars are rare on average. There is only one bright quasar for every few 100,000 normal stars in any given patch of sky. Given their immense distances and the fact that they appear as faint points of light, how do astronomers find quasars among the sea of billions of stars in our own galaxy? Looking for them one by one would be impossible. The search requires clever techniques and massive automated surveys. The primary method for identifying quasar candidates relies on their color. Quasars have a very different spectrum from normal stars. The hot accretion disk means they emit a lot of blue and ultraviolet light. Stars, on the other hand, have a spectrum that peaks at a color determined by their surface temperature. Most stars in our galaxy are cooler and redder than a typical quasar. Large-scale sky surveys, like the Sloan Digital Sky Survey SDSS, take images of the sky through several different colored filters. By measuring the brightness of an object in each filter, astronomers can get a crude measurement of its color. They can then search through the vast catalogs of hundreds of millions of objects for things that have the unusual colors characteristic of a quasar. For example, they look for objects that are very blue. This technique is very effective at picking out potential quasar candidates from the overwhelming number of foreground stars. Another technique is to look for variability. As we have seen, quasars change in brightness. Most stars, on the other hand, have a relatively stable brightness over long periods. By comparing images of the same patch of sky taken years apart, astronomers can identify objects that have changed their brightness, another telltale sign of a quasar. A third method is to look for objects that are bright in radio or X-ray wavelengths, but have a faint star-like optical counterpart. Normal stars are typically not powerful sources of radio or X-ray emission, so any point source that shows up in a radio or X-ray survey is a good candidate for being a quasar. Once a list of candidates is compiled using these methods, the real confirmation work begins. Astronomers must then use a large telescope to take a spectrum of each candidate. This is the definitive test. The spectrum will show whether the object has the broad emission lines characteristic of a quasar, and, most importantly, it will allow a measurement of the object's redshift. If the redshift is large, it confirms that the object is not a star in our galaxy, but a distant luminous quasar. Projects like SDSEs have automated this entire process. Robotic telescopes methodically scan the sky, and software pipelines analyze the data to identify candidates. Then, spectrographs can measure hundreds of spectra at once. This factory-like approach has revolutionized the field, increasing the number of known quasars from a few thousand to over 1 million. It is a process of cosmic detective work using color, variability, and high-energy light to pick out the most luminous objects in the universe from a lineup of ordinary stars. Number 6. The oldest light comes from the youngest quasars. The black hole powering the quasar, J0313-1806, seen when the universe was only 670 million years old, has a mass of 1.6 billion solar masses. According to standard models of black hole growth, there simply was not enough time since the Big Bang for a stellar mass black hole to grow this large. The first stars in the universe are thought to have formed around 200 to 400 million years after the Big Bang. When we use telescopes to look at the most distant quasars, we are looking at the oldest light in the universe. But we are also looking at the youngest quasars, those that formed in the infant universe. And these objects present a profound cosmological puzzle. Surveys have now discovered dozens of quasars with redshifts greater than 6, meaning we see them as they were in the first billion years of the universe's history. These quasars are not small. They are fully formed monsters, powered by supermassive black holes that are already 1 billion times the mass of the sun. This is the problem. How did they get so big, so fast? The standard picture of black hole growth involves 2 main processes. A black hole can grow by accreting gas from its surroundings, or it can grow by merging with other black holes. A stellar mass black hole, formed from the collapse of a massive star, might be about 10 or 20 times the mass of the sun. To grow from 10 solar masses to 1 billion solar masses requires an enormous amount of feeding. The black hole would have to be accreting matter at the maximum possible rate, known as the Eddington limit, continuously for hundreds of millions of years. The problem is that in the early universe, it is not clear that such a steady supply of fuel was available. And even under the most optimistic assumptions, the timeline is uncomfortably tight. There just does not seem to be enough time between the formation of the first stars which create the first black holes and the appearance of these billion solar mass quasars. This has led to a search for alternative theories for the formation of the seeds of supermassive black holes. One idea is the concept of direct collapse black holes. In this scenario, in certain rare, dense regions of the early universe, a massive cloud of primordial hydrogen gas, instead of fragmenting to form many stars, could have collapsed directly to form a single massive black hole seed, perhaps with a mass of 10,000 to 100,000 solar masses. Starting with such a massive seed would give the black hole a significant head start, making it much easier to grow to 1 billion solar masses in the required time. Another possibility involves dense star clusters in the early universe. In these clusters, stars could have collided and merged, building up a supermassive star that then collapsed to form an intermediate mass black hole. This black hole could then have merged with other black holes in the cluster, rapidly growing in mass. The existence of these ancient massive quasars is a major challenge to our models of galaxy and black hole formation. They are a clear sign that something about the early universe was different, and that black holes may have had a more dramatic and rapid formation path than we previously thought. They are clues from the cosmic dawn that are forcing us to rethink the very first chapters of the universe's story. Number 5. A quasar can appear in 4 places at once. The first gravitationally lensed quasar, the twin quasar 2957561, was discovered in 1979. The time delay between the 2 images of this quasar is about 417 days. A famous lens system called the Einstein cross consists of 4 images of a single distant quasar, perfectly arranged around the core of a foreground galaxy. The light from each of the 4 images of the Einstein cross travels a slightly different path, so a flicker in the quasar's brightness will be seen in each image at a different time, over a period of several weeks. The Albert Einstein's theory of general relativity predicts that massive objects warp the fabric of space-time around them. One of the consequences of this warping is that the path of light can be bent as it passes by a massive object. This effect is called gravitational lensing. A massive galaxy or a cluster of galaxies can act as a giant cosmic lens, bending and magnifying the light from a more distant object that lies behind it. While quasars, being both very distant and very bright, are perfect background sources for this phenomenon. When the alignment between a distant quasar, a foreground galaxy, and Earth is just right, gravitational lensing can create some spectacular effects. Instead of seeing a single image of the quasar, we can see multiple images. The gravitational field of the lensing galaxy can split the light from the quasar so that it reaches us along 2, 3, 4, or even more different paths. This results in the surreal sight of multiple quasars in the sky, all of which are actually just different images of the same single object. The Einstein cross is a prime example. We see 4 distinct points of light, the lensed images of a quasar that is 8 billion light-years away, arranged in a cross shape. In the center of the cross is the much closer foreground galaxy, about 400 million light-years away, whose gravity is doing the lensing. Gravitational lensing does more than just create pretty pictures. It is an incredibly powerful tool for cosmology. First, it can act as a natural telescope. The lensing effect can magnify the light from the distant quasar, making it appear much brighter than it otherwise would. This allows us to study quasars that are intrinsically too faint or too far away to be seen directly. Some of the most distant quasars known were discovered because their light was amplified by a foreground lens. Second, the time delay between the different images can be used to measure the expansion rate of the universe, a fundamental cosmological parameter known as the Hubble constant. Because the light for each image travels along a slightly different path through the warped spacetime around the lensing galaxy, the light travel time is different for each path. If the quasar flickers in brightness, we will see that flicker in one image first, and then later in the other images. By measuring this time delay, and by modeling the mass distribution of the lensing galaxy, we can calculate the absolute distances involved, which in turn gives a measurement of the universe's expansion rate. Gravitational lensing provides a unique and independent way to probe the cosmos, using the universe's own gravity as a tool to see farther and measure its fundamental properties. Number 4, they are not forever. The Milky Way's central black hole, Sagittarius A, has a mass of about 4 million solar masses and is currently very quiet. Evidence from X-ray echoes suggests that Sagittarius A may have been a low luminosity quasar as recently as a few hundred years ago. It is estimated that a typical quasar phase in a galaxy's life lasts for only about 10 to 100 million years. This is a very short time compared to the multi-billion year lifespan of a galaxy. A quasar is not a permanent state for a galaxy. It is a temporary phase, a period of intense activity that eventually fades away. The life of a quasar is dictated entirely by its fuel supply. The supermassive black hole is always there at the center of the galaxy, but it only lights up as a quasar when it is being actively fed a large amount of gas and dust. This feeding frenzy is often triggered by a major cosmic event, such as a galaxy merger. When two galaxies collide, their gravitational interactions can disrupt the stable orbits of gas clouds within the galaxies, causing a large amount of material to lose momentum and fall towards the galactic center. This provides a sudden and massive source of fuel for the central black hole, turning on the quasar. But this phase does not last forever. Eventually, the fuel runs out. The black hole consumes the material that is closest to it, and the quasar's own energy output through feedback can help to shut off its own fuel supply by blowing the remaining gas out of the central regions of the galaxy. Once the accretion rate drops below a certain level, the accretion disk cools and dims, and the quasar effectively turns off. The galaxy then returns to a normal quiescent state. The supermassive black hole is still there, but it is dormant, starved of fuel. This means that many, if not all, large galaxies around us today likely went through a quasar phase in their distant past. The evidence is in the supermassive black holes that we find at the center of nearly every massive galaxy, including our own Milky Way. Our central black hole, Sagittarius A, is a sleeping giant. It is currently accreting only a tiny trickle of matter. But if a large gas cloud or a cluster of stars were to wander too close, it could be reignited, and the center of our own galaxy could briefly become an active galactic nucleus, a small-scale version of a quasar. The quasar population has changed dramatically over cosmic time. When we look back to the early universe, about 10 billion years ago, quasars were much more common and much more luminous than they are today. This was the quasar epoch, a time when galaxies were still forming, mergers were frequent, and there was plenty of gas available to feed the central black holes. As the universe has aged, galaxies have settled down, and the fuel supply has dwindled. The bright quasars have mostly faded away. Studying the rise and fall of the quasar population over cosmic history is a key way we trace the evolution of galaxies themselves from their chaotic, gas-rich youth to their more settled gas-poor old age. Number 3, the energy they release is beyond comprehension. A single bright quasar can release more energy in 1 second than the sun will in 10,000 years. The total energy released by a quasar over its 100 million year lifetime can be more than 100 times the gravitational binding energy of its entire host galaxy. Some quasars are so luminous that their radiation pressure alone is enough to overcome the gravity of a star, like our sun, from a distance of over 300,000 light-years. It is difficult to truly grasp the scale of the energy involved in a quasar. The numbers are so large that they lose their meaning, but it is worth trying to put them into perspective. Let's start with our sun. It is a massive nuclear fusion reactor converting about 4 million tons of matter into energy every second, according to E=mc². This produces an enormous amount of power. A typical bright quasar, like 3C273, is about 2 trillion times more luminous than our sun. That is a 2 followed by 12 zeros. Another way to think about it is in terms of galaxies. Our Milky Way galaxy contains a few 100 billion stars. A bright quasar outshines the combined light of all those stars by a factor of 100 or more. Imagine taking 1,000 galaxies like our own and concentrating all of their light into a single point. That is the brightness of a quasar. This energy is not just invisible light. Quasars radiate across the entire electromagnetic spectrum, from low-frequency radio waves to high-energy gamma rays. For many quasars, the majority of their power is actually radiated in the ultraviolet and X-ray parts of the spectrum, which are invisible to our eyes. When we account for all this energy, the total power output is even more staggering. The source of this energy, the accretion disk, is converting mass to energy with incredible efficiency. While the sun converts 0.7% of its fuel's mass into energy, a quasar's accretion disk can convert 10% or more of the mass of the material that falls into it. This is why a relatively small amount of fuel, a few solar masses per year, can produce such a colossal amount of power. The consequences of this energy release are profound. The space around a quasar is a violent and extreme environment. The intense radiation would sterilize any planets for light years around. The winds and jets it drives can reshape the entire host galaxy. The total energy a quasar puts out over its lifetime is enough to completely unbind its host galaxy, that is, to give every single star and gas cloud enough energy to escape the galaxy's gravitational pull. The fact that galaxies survive their quasar phase is a testament to how spread out they are, and how not all of the quasars' energy couples effectively to the galactic material. Quasars represent the most extreme energy generation events in the universe, short of the Big Bang itself. They are a demonstration of the power of gravity, showing how the space-time curvature around a supermassive black hole can be harnessed to create a cosmic engine of almost unimaginable power. Number 2, we are looking at the ghosts of the past. The nearest quasar to us is several 100 million light-years away. There are no quasars in our local group of galaxies. The light we see from the quasar 3C 273, one of the closest and brightest, left its source about 2.4 billion years ago. At that time, on Earth, life consisted of single-celled organisms. When we look at any object in the night sky, we are looking into the past. This is because light, while incredibly fast, does not travel instantaneously. It takes time for light to travel from a celestial object to our eyes. For the moon, it is about a second. For the sun, about 8 minutes. For the nearest star, Proxima Centauri, it is over 4 years. For quasars, this look-back time is not measured in minutes or years, but in billions of years. Quasars are exclusively phenomena of the distant universe. There are no nearby quasars. The conditions in the local universe are wrong for them. Galaxies are old, stable, and have mostly used up their free gas. Galaxy mergers are less common. The era of bright quasars is over. Because they are all so far away, we see them as they were in the distant past. The quasar 3C 273 is about 2.4 billion light-years away. The light that hits our telescopes tonight from that quasar began its journey when the most complex life on Earth was algae. We have no idea what 3C 273 looks like today. The quasar phase may have ended a billion years ago. The host galaxy may now be a quiet, normal galaxy. We are watching a recording of its past glory. For more distant quasars, the effect is even more extreme. A quasar with a redshift of 2 is seen as it was 10.3 billion years ago. The universe was only about 3.5 billion years old. Our own solar system had not even formed yet. The light from these objects has been traveling for longer than the Earth has existed. This is why quasars are so crucial for understanding the history of the universe. They are not just objects in the universe, they are objects from a different epoch of the universe. They provide a direct window into a time when galaxies were young, and the cosmos was a much more violent and active place. We study them not to learn what they are like now, but to learn what the universe was like then. They are time capsules. Each quasar spectrum is a fossil record containing information about the black hole, the host galaxy, and all the intergalactic gas clouds that existed along that line of sight billions of years ago. The fact that quasars are so distant is not a limitation. It is their most important scientific feature. We are, in a very real sense, cosmic archaeologists studying the light from these ancient beacons to piece together the history of the universe. We are looking at ghosts, but these ghosts have stories to tell about the birth and evolution of the cosmos. Number 1. The future is looking at the past with new eyes. The James Webb Space Telescope JUICE is designed to detect infrared light, which is ideal for studying the most distant quasars whose light has been redshifted out of the visible spectrum. The Event Horizon Telescope EHT, a global network of radio telescopes, is working to produce images of the event horizons of more supermassive black holes, giving us a direct look at the central engine of these active galaxies. The next generation of ground-based optical telescopes, like the 39-meter extremely large telescope ELT, will be able to study the host galaxies of distant quasars in unprecedented detail. Our understanding of quasars has come a long way since the mystery of 3C 273's spectrum was solved in 1963. But many fundamental questions remain unanswered. How did the first supermassive black holes form? What determines whether a quasar will be radio loud or radio quiet? How exactly does feedback work to regulate galaxy evolution? The next generation of telescopes and astronomical surveys are poised to answer these questions by looking at the past with powerful new eyes. The James Webb Space Telescope is a key player. Its large mirror and sensitivity to infrared light allow it to see the light from the very first quasars that formed in the universe. JWs can peer back to the cosmic dawn, searching for the seeds of supermassive black holes and studying the galaxies in which they grew. It can analyze the chemical composition of the gas in these early galaxies, providing clues about the first generations of stars. On the ground, massive new telescopes are being built. The extremely large telescope and the 30-meter telescope will have mirrors so large they can collect enough light to study the faint host galaxies of quasars in detail. For a long time, the quasar itself was so bright it was impossible to see the galaxy it lived in. These new telescopes, with advanced adaptive optics to correct for atmospheric blurring, will be able to separate the light of the quasar from the light of its host, allowing us to study the relationship between the two directly. Radio astronomy is also making huge leaps. The Square Kilometer Array SKA, when completed, will be the world's largest radio telescope. And it will be able to survey the sky with unparalleled sensitivity, detecting even the faintest radio jets from distant quasars and mapping the distribution of hydrogen gas throughout cosmic history. The Event Horizon Telescope continues to refine its techniques, hoping to image the shadow of our own galaxy's supermassive black hole, Sagittarius A, and perhaps other nearby targets. These images provide a direct test of general relativity in the most extreme gravitational environment and give us a close-up view of the physics of accretion that powers all quasars. The future of quasar research lies in combining data from all these different facilities. By observing quasars across the entire electromagnetic spectrum, from radio waves to gamma rays, and by using new technologies to see farther and with greater clarity, we can piece together a complete picture of these extraordinary objects. They were once impossible puzzles, but they have become our most powerful tools for understanding the history and evolution of the universe. They are the brightest lighthouses in the cosmic darkness, and we are just now building the telescopes we need to truly understand the shores they are illuminating.